Hello, today we're going to talk about structure 2.2.13 and 2.2.14. This is a higher level only topic. We're going to talk about expanded octets for Lewis structures and formal charge. Okay, so when you're drawing these covalent compounds and their Lewis structures, if you have an element, central element, that is in the third period or lower, you can actually form an expanded octet where it has more than 8 electrons around the central atom. And the reason for that is that it involves the D block. That's why it has to be in the third period or lower, so you can involve the 3D sublevel. You don't need to really understand why or how exactly it does that, just that third period elements and below. So that's like things like phosphorus. So let's look at an example. If I have phosphorus pentachloride, let's go ahead and solve this using the normal Lewis structure method, where you're going to add up the valence electrons. Phosphorus has 5, chlorine has 7, and there's 5 of them, so that's 35. Total valence electrons is 40. You always put the first one in the center, so phosphorus in the center, and you have 5 chlorines on it. So already you're seeing that the phosphorus has 10 electrons around it right now. 2 for each of the bonds. So I used up 10 electrons there. I have 30 to fill in the octets of the outer atoms. So each chlorine right now only has 2, and it needs to have 8. So 1, 2, 3, 4, 5, 6 additional on each of them. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 6, 7, 8, 9, 30. So I used up all 30 of those valence electrons. And so this is my Lewis structure for PCl5. And it works because phosphorus is in the third period, and some of the electrons are going to be using some d orbitals to do some of the bonding here. You just don't necessarily need to understand exactly how that happens, just that it does. Let's do one more example. Let's do xenon tetrafluoride. So for the same reason, you can even get noble gases to form some of these covalent structures, because you're involving some of these other orbitals. Whereas typically you don't see things, noble gases are not usually forming those bonds. So it's more difficult for, like almost impossible for helium and neon, because they are not in the third period. But xenon does form some compounds. And so let's look at xenon tetrafluoride. Xenon has 8 valence electrons, fluorine has 7, and there's 4 of them. And so total, that's 36 valence electrons. And I'm going to put xenon in the center, and I will put my 4 fluorines around the outside. And I just made 4 bonds, so I used up 8 of electrons. I have 28 left. I need to use those to fill in the octets of the outer atoms first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24. So I used up 24 to fill up those octets. I have 4 left over. Well, anytime you have leftover, you have to put them on the central atom. So I have 2 lone pairs on the xenon, which gives xenon 12 electrons around the center there, which is a lot more than 8. So it definitely has, so it definitely has more than the octet. It has that expanded octet, which it's allowed to do because it's in the third period or lower. Okay, so because you can have atoms with expanded octets, we also have 2 new geometries we need to talk about. And the first one is going to be trigonal bipyramidal. And I'm going to draw this as best I can in 3D, but effectively you have your central atom, and around the center you're going to have 3 atoms around like the equator. So imagine that you have like a planet and around the equator there's 3 sticking out. I'm going to draw 1 going back, 1 coming forward out of the page, and then 1 in the plane of the page. I don't know why I circled that. There we go. So 3 around the center, and then you have one coming straight up and one going straight down. And so that would be trigonal bipyramidal, where you have 5 electron domains around the center. So it's trigonal bipyramidal. Now, if all of those are atoms, its molecular geometry is the same as the electron domain geometry, which is trigonal bipyramidal. If you have one of them is a lone pair, one of those equatorial atoms is going to change into a lone pair. So let's say it's here, lone pair. Actually, let's draw that a little nicer. Lone pair. Like this. And this is called a seesaw, which is kind of fun, where you have 4 atoms and a lone pair. If you have 2 of them are lone pairs, then you'll have 2 lone pairs like this. That is called a T-shape. And finally, if you have 3 of them that are lone pairs, it will just be linear because all of the equatorial ones are gone. So again, all 4 of these have trigonal bipyramidal electron domain geometry because there's 5 areas of electrons, but they have different molecular geometries because you have to look at the difference between atoms and lone pairs for that. So the bond angles for these molecules is different depending on which atoms you're comparing. If you're comparing the 2 axial atoms, or the 2 that are right across from each other, that's 180. Okay, so just like for the linear, that would be 180. If you are comparing an axial to an equatorial, I'll draw it here. So like these 2 atoms, that would be a 90-degree angle. Or if you're comparing the atoms that are all equatorial around the center, right here, because it forms like a triangle around the center, that becomes 120 degrees. So you have 180 degrees, 90 degrees, and 120 degrees, depending on which atoms you're comparing. So be careful. It's a little difficult for them to ask this question because of those different bond angles, but it's not necessarily out of the realm of something that they could ask. There's one other VSEPR geometry that becomes possible with expanded octets, and that is octahedral. Octahedral, you have your center atom, you have 2 axial atoms, and you have 4 equatorial. Like this. And so you have 6 electron domains. And if all 6 of those are atoms, then the molecular geometry is the same as the electron domain geometry, which is octahedral. If you have one of them as a lone pair, what happens is one of the axial ones is the lone pair. Like this. And so this is called square pyramidal. Square pyramidal. If 2 of them are lone pairs, then both axial ones are gone. And your lone pairs are like that. And this one is called square planar because all 4 of the remaining atoms are in the same plane. And then if you had 3 of them, it would be T-shaped. Let's see if I can draw that. And then if there were 2 of them, it would just be linear. Which would be weird to see, but there you go. So label these T-shaped and linear. And for the bond angles here, it's either going to be 180 degrees for the ones that are directly across from each other, or 90 degrees for the ones that are adjacent to each other. And so really, you just have to look, is it on the opposite side or is it adjacent? And so it depends on whether it'll be 180 or 90 degrees. And I would recommend, if you can, make models of these so you can see them in a little bit better structures without me trying to draw it in a 2D plane, because they are three-dimensional structures. So build a model or build a simulated model so you can see for both the trigonal bipyramidal and the octahedral ones, see the structures, get a feel for how they would look in real life. So the other thing we're going to talk about today is formal charge. And really it's for, sometimes you have Lewis structures that can be kind of ambiguous on which one is the better structure. Like you might have different places to put double or triple bonds. We use formal charge to find the most stable structure. I'm going to use a simple example first to show you kind of how it's done. And so let's look at CO2. So let's say we're going to do these two different structures where all of the atoms have their full octet. Octet rule is satisfied. Which one is preferred? Now, again, I say this is a simple one because we know carbon dioxide is this structure, but let's look at why using formal charge. To do formal charge, you need to basically list the normal amount of valence electrons for each of the atoms. So the typical amount for oxygen is 6, and the normal amount for carbon is 4. Okay. And then what you do is you take what we call the number of electrons assigned to it. So for bonds, you count one electron for each bond. But for lone pairs, you need to count each dot. Each electron counts for 1. So let's look at the carbons first. Carbon has 4 bonds on it. Each bond counts as 1. So that would be 4 for that carbon. There's no lone pairs. The other carbon also has 4 bonds. So we count that as 4. Now let's look at oxygen. This first oxygen here has 2 bonds and 4 electrons in lone pairs. So that's 6 total. Again, that would be, let me use a highlighter here. 1, 2, 3, 4, 5, 6 for that oxygen. Okay. For the other oxygen, same idea. We have 2 bonds and 4 electrons, so that would be 6 as well. For the next oxygen down, I have 3 bonds this time and 2 electrons in a lone pair. So that's 5. My very last oxygen down here, I have 1 bond plus 6 electrons in lone pairs. So that's 7. And then what you do is you subtract. Okay. So the normal valence electron minus the electrons assigned to it gives us 0 for the first oxygen, 0 for the first carbon, 0 for the second oxygen there. The next oxygen down, it would be plus 1, because 6 minus 5 is plus 1. 0 for the carbon, and then 6 minus 7 is negative 1. So the best structure, the best Lewis structure, is the one that minimizes the formal charges present in the compound. So you want them all to be 0 if possible, which is why this structure for carbon dioxide is the more stable one. All of them are 0 formal charge. They all have the number of electrons that they want to have the most stable structure. In our other structure here, the oxygen with the triple bond has a formal charge of +1, and the oxygen with a single bond has a formal charge of -1, which is less stable. Now, sometimes you can't get them to the point where they're all 0. Sometimes that just happens. In which case you want the negative charge. Let's see if I can write this. A negative charge should be on the more electronegative atom. So we're trying to get the lowest numbers first, and if you can't get them all to 0, then any negative charges need to be on an atom that has more electronegativity. And so that's kind of your hierarchy of which one you're choosing is more stable. Okay, for this question we want to predict the shape and bond angle for PF6. So I need to draw the structure. Phosphorus has 5 valence electrons, fluorine has 7, and there's 6 of them, so it's 42. Plus there's 1 additional electron for the negative charge. So that gives us 48 electrons total. Phosphorus is in the center, and there are 6 fluorines going to go around the outside. So I just made 6 bonds with 2 electrons each. So I'm left with 36 valence electrons, and I need to fill in the octets of the outer ones first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Great, I used up all of them, so I don't have any extra to put on the center. So that phosphorus has 6 atoms around it, giving it an octahedral electron domain geometry, also an octahedral molecular geometry. And because of that, there are 2 bond angles in here. Atoms that are opposite of each other have 180 degrees, and the fluorines that are adjacent to each other have bond angles of 90 degrees. So like the difference between these two, the angle between those 2 fluorines would be 180, but between these 2 would be 90 degrees. Okay, so for this question, which of the following structures of XeO3 is preferred? We need to use formal charge for this. So xenon, let's do the xenons first so we can see. Xenon has 8 because it's a noble gas normally. And right now it has 1, 2, 3, 4, 5, 6 electrons assigned to it. So 8 minus 6 gives us a formal charge of +2 on that xenon. For the other xenon, it still has 8 normally, but right now it has 1, 2, 3, 4, 5, 6, 7, 8 assigned to it. So 8 minus 8, that's 0. So already looking at just the xenon atoms, it's looking like this structure might be the preferred one because of the formal charge of 0 on the xenon. But let's double check the oxygens. Oxygen normally has 6 valence electrons. If you have a structure that has 2 lone pairs, 2 bonds and 2 lone pairs, that gives us 6 total for an oxygen. And so 6 minus 6, oops, I'm drawing, there we go, 6 minus 6 gives us a formal charge of 0. So all of those oxygen atoms that have 2 bonds and 2 lone pairs have formal charges of 0. The ones that have just 1 bond and 3 lone pairs, they normally have 6, and right now there's 7 electrons assigned to it. 6 in lone pairs and 1 bond, so that gives us a -1 formal charges for both of those oxygens. So this structure is the preferred structure because all of the formal charges are 0. So that gives us our answer there, and that would be your explanation and justification as well, is that this structure is preferred because all of the formal charges are 0. We talked about this a little bit, the ability of some atoms to expand their octet. It has to be in the 3rd period on the periodic table or below, because then they have access to the 3D sublevels, or 4D or 5D or whatever it is. But you do not, 2D doesn't exist, 1D doesn't exist, so you have to be in the 3rd period or below to have that expanded octet available. So one thing when you're calculating formal charge is you are counting the normal number of valence electrons and the electrons that are assigned to it. So an assumption when it's talking about this is when you have a bond, right? Let's draw this using the actual electrons. Like this. There are 4 electrons being shared in both of those double bonds. When we're assigning a formal charge, we assume that 2 of the electrons are assigned to carbon and 2 of them are assigned to oxygen, so that it's sharing them evenly. And in reality, that's not necessarily true, because the more electronegative atom is going to attract them more than the less electronegative atom. But for the case of formal charge, it's just a tool for us to be able to figure out which thing is more stable or less stable. It's not an accurate description of how the electrons are being shared in those bonds. So that's what it's talking about with assumptions here. We do something similar for oxidation states. It's not a true charge. It just helps us track to see how it's gaining or losing electrons. Yeah, so it's a useful tool. It just doesn't maybe tell us exactly what's happening with the electrons themselves.